Hello, this is Dr. Vev. This video, we shall be discussing the very important divergence theorem of Gauss and related applications of the same. So we'll start off like we did the previous video with a basic computation. In this case, you're asked to find the flux of the vector field specified here. It's got the x and the y components, and it's not got the z component to keep things manageable. Alpha and beta are any two real numbers. And we want the flux through the surface of an ellipsoid. So the ellipsoid's upper surface, to be specific, it's given by the equation x squared over a squared plus y squared over b squared plus z squared over c squared equals 1. Sometimes this is called a scalene ellipsoid because all three sides are unequal. A union z equals 0, which means that we also consider the bottom part of the hemisphere. The top part and the bottom part is flat. So this is going to be an hemispherical ellipsoid, and it's a closed surface, which is noteworthy. So we'll find the flux just in a honest, simple-minded fashion. It's going to be a hard calculation, so brace yourselves for the calculation. So let's just recall what's meant by the flux of a vector field. You've probably studied this in earlier classes involving electricity and magnetism, where you had things like the electric flux and a magnetic flux and so on. There, your instructor would have told you that flux is a scalar, and it measures something like the amount of field lines that goes through the surface, and in turn, it is a measure of how strong the field is. So the flux of a vector field is a mathematical quantity and can be defined as follows. Phi, that's a flux through a closed surface. That's phi sub c, is going to be the double integral, oriented double integral over the surface of the vector field dotted with a normal to the surface, n hat, times the area element to the surface, d sigma. So that's the basic definition of the flux that we're going to have to use. Let us draw a basic picture of the ellipsoid. Now, I warn you, this is not going to be a pretty sketch. I'm reasonably confident about drawing a sphere. So let's see how this turns out. I'm going to, for security, mark out that's A, it's minus A, and then that's B, trying to make A, B, and C look different, and that is C. Okay, so the ellipsoid. Not easy to draw. And then for the, maybe I'll draw another section. This is the ellipse section that's cut by the XZ plane. And then I'll draw another ellipse section that's cut by the ZY plane. So that'll sort of, the three things together will make it look more like an ellipsoid. So I hope that makes sense, like a dome, okay? Plus that also includes the bottom surface. The electric, or rather the, I keep calling it the electric field because that's the most common application of flux. So don't mind me if I say electric field accidentally. The vector field here is F, and F is alpha x plus beta y. So we sort of know that it's going to be parallel to the XY plane. So I'll just draw the F in one or two places. Well, it also means that we don't have to worry about the flux through the bottom surface, because the bottom surface, which I'll call N, the normal vector of the bottom surface is N2, and I'll call the bottom surface itself S2. We don't have to worry about that because the dot product of F and N2 will be 90 degrees, cosine of 0, because this F is going to be on parallel to the XY plane. So we only have to worry about this, the hard stuff, the normal vector N1 to the surface, the curved surface S1. And that's what we'll focus our attention doing here. So this is just equal to S is the union of S1 and S2. And so this is going to be written as the open integral of, now by the way, the orientation symbol means that you're choosing an orientation of the normal vector. In this case, I'm choosing the outward normal orientation. The way it's defined as follows. You take a small patch on the surface and you go around it using your right hand rule, and then the fingers of the right hand tell you how you're moving, and the thumb basically gives you the direction of the normal vector, which in this case is outward normal, and the same down there. If you go around a little loop, it'd be more like this loop, then the outward normal would be that. So that comes from your right hand rule. So once you have that normal convention chosen, you don't have to put that symbol anymore. And then here I have S1. The only surviving component is S1, F dot N, N1 times d sigma 1. So that is what we're going to do. We have to find out what N1 is. We need to find out what d sigma 1 is. Now, we have to have a way of parameterizing the ellipse. Spherical polar coordinates are probably the best bet. So what we're going to do is we take some point here and imagine drawing a radius vector. Then that point, when projected down, is going to give you the coordinates x, y, and z. Okay, so we're going to use the same coordinates as we have in spherical polar coordinates. That's going to be our theta vector, theta angle, and from the x, you're going to have the phi angle. So our parameterization is guided by that. I mean, I can't think of anything else. So that's really what I can think of. So I'm going to write x equals a cosine phi sine theta. Well, that makes sense because if I do this projected down, it's going to be a sine of theta, and then that's going to be cosine phi in the x coordinate. The y coordinate is going to be b times sine phi sine theta, and z is going to be c cosine theta. Now, just to save space, I'm going to adopt the notation. This is a space-saving notation. It's not earth-shattering. I'm going to call c for cosine and s for sine. So a cosine phi sine theta, and that's going to be b sine phi sine theta. And here, be careful, c times cosine theta, because there are two c's. I'll try to separate them out. I'll put a dot or something in between just so you don't get confused, okay? So that's going to be my space-saving notation. It'll really save a lot of space. So now we have to think about how to define the normal vector n1. Well, n1 is, the direction of the n1 is given by the direction of gradient. So we have to use the fact of the gradient of the function phi that defines the surface. The surface is defined by the function phi. In fact, the function phi is right there. So divided by, you want to make it a unit vector, so you divide it by the norm, or the size of the gradient, if you like. So this phi function, let's write down what it is. Phi of x, y, z is going to be x squared over a squared plus y squared over b squared plus z squared over c squared minus 1. The reason I write like that is because then phi equals 1 will be the desired surface. Phi equals 0 will be the desired surface, S2, S1. So when you put phi equals 0, I get this is equal to 0, and I can transfer the 1 to the other side. It'll become exactly equal to that. So that is the way we define the phi function. Now the gradient is, recall what that is. It's I hat del by del x plus j hat del by del y plus k hat del by del z. So when I differentiate, this picks up only the first term, this picks up only the second term, that picks up only the third term. Now, instead of writing I hat, j hat, and k hat, I just like to use commas to separate out my components. So let me use that notation here. So n1 hat becomes, when I differentiate with respect to x, I get 2x. So I'm going to get 2x over a squared, comma, 2y over b squared, comma, 2z over c squared, divided by the norm, which is going to be the square root of all these things squared. So the 2's are common, so I'll bring the 2 outside. So I'm going to get x squared over a to the 4 plus y squared over b to the 4 plus z squared over c to the 4. That 2 will cancel out the 2's here. Well, unfortunately, now we have to substitute our coordinates in there. So let's do that. X is, when I put x equals a cosine theta sine, a cosine phi sine theta, the one factor of a will cancel out. So I'm going to get cosine phi sine theta over a. Similarly, I get sine phi sine theta over b, and then cosine theta over c. Please don't be tempted to cancel out the c's here. That's cosine theta, and that's the number c. That's the slight danger with this notation. Okay, now you have to just square whatever you have above. So that's cosine squared phi sine squared theta over a squared plus sine squared phi sine squared theta over b squared plus cosine squared theta over c squared. Now what I'm going to do, because I don't like these ABCs, is I'm going to multiply the numerator and the denominator by the product ABC. Then I'll get rid of ABC in both places. So let me try doing that. Just keep this calculation here so you can see it. Just continuing, n1 hat is equal to BC cosine phi sine theta, comma, AC sine phi sine theta, comma, AB cosine theta, divided by the same things squared. Just in case you're getting a little panic attack looking at the denominator, rest assured that by some miracle of multivariable calculus, the denominator will somehow cancel out at the end. Okay, so this is what I'll call n1 divided by the magnitude of n1. That's the unit vector n1. Now we have finished the hard part. Now let's look at d sigma 1. If, again, remembering your multivariable calculus, that is given as the r theta, I'll explain what that is, cross r phi d theta wedge d phi. If you don't know what the wedge product is, don't worry about it. It's just an antisymmetric product. It tells you that the area has got a sign, basically the sign given by the cross product, and it ties into the orientation by the outward normal. If you don't like that wedge, just don't think about it, but I like to write it. It's an antisymmetric oriented area element. That's what it is. Now, what is this R? R is a vector. That's basically the position vector, x comma y comma z. So x is going to be a cosine phi sine theta. Y is b sine phi sine theta. And z is c cosine theta. Now, when I say r sub theta, what I really mean is the derivative. So r theta is the partial derivative of r with respect to theta. That's what it really is. So let's calculate what that is. Then I get a cosine phi cosine theta, and then b sine phi cosine theta, and then that's negative c sine theta. R sub phi is the partial derivative of r with respect to phi. So that's going to be negative, because when I differentiate cosine, I get negative sine. So a sine phi sine theta, b cosine phi sine theta, 0, because that term does not depend on phi at all. Now we just have to find the magnitude of the cross product. The cross product itself is a determinant. So the magnitude of the cross product will be the magnitude of the determinant. So for simplicity, I write it in a compressed notation. The determinant itself is single square, single vertical bars. When I put double vertical bars, I mean take the determinant and then take its magnitude, okay? So that's going to be I hat, j hat, k hat, that's what the determinant is. R theta next, which is this stuff here, a cosine phi cosine theta. And then I'll copy this down for R phi. Keep in mind all the struggles we're going through to do this, because very soon I'll talk about Gauss's divergence theorem and how the right-hand side is almost always easier to do than the left-hand side. We're doing the left-hand side. The dreaded calculation, the difficult calculation is the left-hand side. So this can be calculated. I hat will give me this times this minus this times this. So I'm going to get the magnitude of I hat, which is be left with positive BC squared Is that right? No, there's no. I succumb to my own notation here. That is b cosine phi, and that is c there. So it's bc times cosine phi sine squared theta. So you can see the pitfalls of this notation. Minus, because of that determinant thing. Remember, the determinant comes with this assignment of signs, like that. Now what? It's going to be this times this, which is 0, and that's minus this times this. So it's going to be minus a times c. Separate this out like that. Sine phi sine squared theta. And then the k hat term is going to be the big deal, because it's going to have 2 terms. So let's be careful there. Plus k hat. So that's going to be AB. And I'm also going to get AB there. So I'll take AB common and put a flower bracket here. AB cosine squared theta, sine theta, cosine theta, cosine squared phi, sine theta, cosine theta. Plus sine squared phi sine theta, cosine theta. Close parenthesis, close norm, d theta wedge d phi. All right, almost there. The norm is the square root of the square of everything inside. So let's do that. By the way, here you notice that sine squared plus cosine squared is 1. So we don't have to worry about that. Just write this last term as AB sine theta, cosine theta. Now there's a sine theta, cosine theta term here, and there's a sine squared theta and a sine squared theta. So I can take sine theta outside before taking the norm. I'll do that. So then I'll take the norm. So I've taken the sine theta outside, keep that in mind. If I've taken one sine theta outside, I just have cosine phi sine theta here. And so I'll get b squared c squared cosine squared phi sine squared theta plus a squared c squared times sine squared phi sine squared theta. Remember, there's only sine theta here because I've taken a sine theta out. And then over here, the sine theta is gone. So I only have cosine theta left. So I get a squared b squared times cosine squared theta times sine theta d theta wedge d phi. That's the sine theta I took outside. But observe the top calculation. This is the miracle I was alluding to. The denominator there is exactly the same as this. So you believe in miracles? I do. So this is just outstanding. So this is just equal to the magnitude of n1 times sine theta d theta d phi. You can show, generally speaking, that this is always true. It's a theorem in surface theory, if you like, but I don't like to quote theorems. I like to see things in calculation, especially things like this. You may or may not remember the theorem from multivariables. So if I say it's a theorem, you may or may not believe me, but now you see it actually works. With all this in mind, let's now calculate the flux. That's the last thing we have to do. So what is the flux? Flux to the closed surface is just going to be the integral S1 F dot N1 d sigma 1. And we have all the ingredients to calculate this object. So let's do it. So it's the integral over S1. The vector field is alpha xi hat plus beta yj hat dot product with. Now, because n1 in the denominator will cancel the n1 here, I won't even bother writing it. I'll just write the numerator, which is all this stuff. BC times cosine phi sine theta, comma. Well, I don't want to use comma now because I've already committed to I hat and j hat. So let me switch to I hat and j hat. I hat plus AC sine phi sine theta j hat plus AB cosine theta k hat times sine theta times d theta d phi. I'll forget about the wedge now. This is just I hat will only contribute with this, will only pair with this, j hat will pair with that, k hat is left alone, doesn't make a contribution because there's no k hat over there. So I'm left with the integral over the surface S1 alpha times. Now for x, I'm going to write AC a cosine phi sine theta And then I have to multiply it with this. So that gives me BC times cosine phi sine theta plus beta times y, which is B sine phi sine theta times this. The whole thing multiplied by sine theta d theta d phi. All right. Now you'll notice that there's A, B, C here, A, B, C here. So you get A, B, C outside. They're just constants, can be brought outside. The other thing you have to notice is that phi, let me just write one more step. Alpha cosine squared phi sine squared theta plus beta sine squared phi sine squared theta times sine theta d theta d phi. So I can take sine squared theta common, and I have ABC. I can split up also the theta and the phi integrals. So the phi integral is 0 to 2 pi, because phi goes all around the ellipsoid like this. 0 to 2 pi alpha cosine squared phi plus beta sine squared phi d phi. And then I have integral theta equals 0 to pi by 2. Pi by 2 is because it's just upper half of sine cubed theta d theta. Because you have sine squared times sine cubed. That is our double integral. It's rather easy to do this. The integral from 0 to 2 pi of cosine squared phi is just pi. If you don't believe me, I'll quickly calculate it for you on a rough sheet. That's my rough sheet here. Integral 0 to 2 pi of sine squared or cosine squared, really, it's the same thing, d phi. Well, you can write sine squared as, so there's an identity, and that is the half angle identity. Cosine squared theta minus sine squared theta, cosine squared 2 phi. Cosine 2 phi is cosine squared phi minus sine squared phi. Let's just go like that. And cosine squared phi is 1 minus sine squared phi. So that's going to be sine squared phi. So this gives me 1 minus 2 sine squared phi. These are the famous half angle identities. So that tells me that sine squared phi is just going to be 1 minus cosine 2 phi divided by 2. And now if I have that, I'll get 1 minus cosine 2 phi divided by 2 d phi, integral 0 to 2 pi. And that's just half times 2 pi minus the integral of cosine 2 phi, which is half of sine 2 phi. Sine 2 phi divided by 4. And then when I take the limit between 0 and 2 pi, that vanishes. So the answer is just pi. Okay, and the same thing for cosine squared. So that's a well-known averaging procedure. So I get pi times ABC, alpha plus beta, And the integral of sine cubed, that's the only remaining headache. Well, I can write that as sine squared times sine, and sine squared is 1 minus cosine squared times sine theta d theta. So that's almost the home stretch here. We don't have very far to go. Now I just do a U substitution on this one. I'll say U equals cosine theta, and then negative sine theta d theta will be du, and so on. So let me just write down pi ABC alpha plus beta. The integral of sine theta is negative cosine theta, and that gives me positive cosine cube theta over 3 when I do the U substitution. From 0 to pi over 2. There's no contribution at pi over 2 because cosine vanishes. There's only contribution at 0, so that reverses the sign of this and reverses the sign of that. So I get 1 minus 1/3, which is 2/3. Amazing. That's the answer. So that was a lengthy calculation, probably took half an hour. I'm not checking my time. Probably took half an hour. Now let's introduce Gauss's law, or Gauss's divergence theorem. This is one of the reasons Gauss is regarded as the top 3 mathematicians of all time, the others being Newton and Archimedes. So you can see how well separated they are in time. And most mathematicians agree that there's been no such greatness after Gauss. So it's quite a great mathematician he is, or he was. His fame rests on many, many things. One of them is the divergence theorem. What is it? For sufficiently smooth fields, the restrictions on the divergence theorem are not as much as it is for Stokes' theorem, but you still have to have all the smoothness things. I won't bother rattling off those things. The divergence theorem says if you have a vector field that's reasonably smooth, defined everywhere in space, then the flux, which is the integral of the vector field f dot n, what we just did, d sigma over the surface S, which is the boundary of a volume V, is the same as the triple integral over the volume V of the divergence of f times the volume element d tau. This is called the divergence theorem because this quantity here is the divergence of the vector field, sometimes simply called div f. So what we did in the first part of the video was to calculate this. This is what we just did. Well, let's try this. It'll turn out to be an easier calculation. Mind you, it's not stupid easy, but it's easy. Easier, I should say. The problem with this calculation is that you still have to find the volume element. So the volume element is not that simple to find for something like an ellipsoid. So that's the only trick, or the tricky part, okay? So let us go about doing that volume element calculation. What is this d tau? Well, d tau is going to be dx wedge dy wedge dz. Pretty complicated triple wedge product, and we don't want to get into doing that. So what we'll do is a clever transformation. We'll change from the coordinates x, y, z to the coordinates u, v, w. This goes back to how do you make a ellipsoid look like a sphere? You can choose meter sticks that are different in different directions, such that they all agree to measure a circle instead of an ellipsoid. So that's really what's happening. These are called scaling transformations. And the scaling transformations, which means you're choosing 3 different rulers in 3 different directions, is x equals AU, y equals BV, and z equals CW. With the scaling transformation, we can work out the volume element, which is dx wedge dy wedge dz. The new coordinate system is just given by the Jacobian xu, xv, xw, yu, yv, yw, zu, zv, zw, the Jacobian determinant times the volume element in the new coordinates, which is simply that of a sphere. Now, these subscripts refer to partial derivatives. So x sub u is going to be a, and then x sub v is going to be 0, and x sub w is going to be 0 because x does not depend on v and w. Similarly, the only terms that survive are y sub v, which is b, and z sub w, which is c. Everything else is 0. So I get d tau equals the determinant of a 0, 0, 0, b 0, 0, 0, c times du wedge dv wedge dw. And that's just ABC times du wedge dv wedge dw. When I integrate both sides, integral of d tau, triple integral actually, is the volume of the ellipsoid. And that's going to be ABC times the volume of a sphere. Well, the volume of a sphere is 4/3 pi r cubed, but r is 1, it's a unit sphere. Why is it a unit sphere? Because when you write the ellipsoid in the new coordinates, you're going to get u squared plus v squared plus w squared equals 1. So it's a unit sphere with radius 1. So we have found the volume of an ellipsoid, which is 4/3 pi ABC. For a semi-ellipsoid, you get 2/3 pi ABC. So just keep that in mind. Now let's calculate also the divergence, which we need to apply. So what's the divergence of f? That's just going to be del x fx plus del y fy. Remember, our vector field f is alpha x I hat plus beta y j hat. There's no z component, so the divergence has just got 2 terms. And that's just going to be alpha times the derivative of x with respect to x, which is 1. So this is just alpha plus beta. I hope that rings a bell. That's the alpha plus beta we have here. And the 2/3 pi ABC is just the volume. We're done. So the right-hand side of Gauss Law tells us that the triple integral volume del dot f d tau is just alpha plus beta times the triple integral over the volume d tau. And that's alpha plus beta times the volume of an upper ellipsoid. That's going to be half that volume. 2/3 pi ABC. A much simpler calculation, if you don't mind my saying so, although the first calculation did have its pretty moments and surprises, such as the cancellation of the norm of the normal vector. For the second part of our video, we'll talk about Gauss's laws in physics. There are many of them, as you already know from having studied E&M theory. Basically for E&M, let's recall what that is. E&M, the law of electricity is known as Coulomb's law. That tells you the electric field of a point charge is K times Q over R squared R hat. This can also be written in terms of the divergence. So the divergence of the electric field, del dot E, is going to be equal to the quantity known as the charge density rho divided by epsilon naught. And when you, this is the equivalent form as that one, okay? Now, when you take the volume integral on both sides using the surface integral on both sides, I'm going to get the surface integral S equals del V. I'm copying down that really of E dot N d sigma. So the flux through the surface, the electric flux through the surface will be equal to the triple integral of the volume of the divergence of the electric field times d tau. The divergence of the electric field is just the charge density rho divided by epsilon naught. So I'm going to get epsilon naught as a constant. The triple integral over the volume of the charge density times the volume, which is known as the total charge. So that's the enclosed charge in the volume divided by epsilon naught. That's the famous Gauss Law in University Physics 2 that many of you have studied quite extensively. Can we find a similar law for gravity? So this is where we work by analogy. There's nothing more powerful in physics than analogy. So by analogy, let's look at gravity next. Gravity proceeds by the famous law of Newton, regarded by some as the greatest single leap of imagination, looking at an apple fall and then looking at the moon at the same time and realizing the same law applies to both. So that's Newton's gravitational constant. The force of gravity is Newton's gravitational constant times the mass of the first object. We'll call that mass the test mass, times the mass of the main object, that'd be like the Earth. Okay, the test mass is like the moon or the apple, divided by r squared. And because I put a vector sign, I have to put some put a negative r hat because it's always attractive. All right. So that's the gravitational force. The gravitational field is a force per unit mass. So the gravitational field G, just like the electric field is electric force per unit test charge, the gravitational field is gravitational force divided by test mass. When I divide by m, I'm just left with negative G sub n m over r squared r hat. So that's the gravitational field in for a point particle or a spherically symmetric object. So that's what we have to work with. Now observe the similarity between the gravitational field of a regular mass and the electric field of a negative charge. A negative charge will have the same electric field as a gravitational field. A negative charge will suck all the positive test charges toward it. And the gravitational field behaves the same way. I won't draw the picture, it's the same picture. So how do we write down Gauss's law for this? For convenience, it is sometimes G sub n times m is sometimes taken to be called gamma. So this is gamma over r squared times r hat. So the divergence is going to have this epsilon naught is 1 over 4 pi k. All right. Now I'm going to stick with, for now, I'm going to stick with G sub n just to write down the analogy, and then I'll use gamma when necessary. So let's try to find an analogy here. So k times q is exactly like G sub n times m. So I have replaced the divergence q by rho. That's easy to understand. So I can replace in the divergence theorem for gravity m by the mass density rho. Now I've replaced also k by 1 over 4 pi epsilon naught, and the 4 pi disappears. Okay, so k equals 1 over 4 pi epsilon naught, and the 4 pi disappears. So here I have G sub n. I don't have anything like an epsilon. So if I were to write K as 1 over 4 pi epsilon naught, the epsilon naught here would be 1 over 4 pi K. So let me just rephrase this. Divergence is equal to 4 pi K times rho. That's an equivalent way of thinking about it. This way you don't have to introduce this quantity epsilon, okay? Now that's exactly where it is. So all I have to do is multiply whatever is multiplying the law of gravity with 4 pi and I'm done. So I've discovered the law of the divergence theorem for gravity. Del dot G equals 4 pi Gn times the mass density rho. And then if you apply divergence theorem to it, we can find out the gravitational flux. So let's do that. The double integral of the surface, which is the boundary of the volume of G dot N d sigma is going to be the triple integral of V, the divergence of G, d tau. The divergence of G is just 4 pi Gn. So I can write this as 4 pi G sub n times the triple integral of the volume of rho d tau. The only one thing I forgot, I realized as I was writing that, is a negative sign. So don't forget the negative sign. It's there. Gravity is always attractive. The attractive or repulsiveness in the electric case comes from the sign of Q. If Q is positive, then it's repulsive. That'll be like anti-gravity. And if Q is negative, it'll be attractive. That's like regular gravity. So that's our Gauss's law for gravity. Let us see if it works. The simplest way to see if it works is to test it for a point mass. If you have a point mass, then by symmetry argument, the gravitational field is going to point radially inwards everywhere. So the left-hand side of Gauss's law can be simplified. Left-hand side is going to be the double integral oriented G dot N d sigma. Well, the normal vector is actually outward pointing in this case. So we could have got the negative sign like that. But here I already know that G is pointing inwards. So in this case, I already have the benefit of knowing that G is pointing inwards. If you did not know, you need the negative sign. So I don't really have to have the negative sign there in this case. So G dot N d sigma is going to be equal to 4 pi Gn. Well, the density is just going to be the charge times the delta function, which vanishes everywhere except at the origin. So when you integrate it, you're just going to get the mass m times the volume d tau. D tau is the volume. So that's we'll wait on that. It's we'll just say it's the volume of a sphere. So it's 4/3 pi r cubed. That's what it is. On the left side, the G dot N is going to be cosine 180. So I'm going to get the magnitude of G times cosine 180 times d sigma. The integral over d sigma is just 4 pi r squared. So that's I have an extra 4 pi, and that comes from the definition of the delta function. The delta function, when you integrate it over all of the volume, gets rid of this 4/3 pi. So that's how you get rid of that. So let me just say the integral of rho d tau it's just Q. There's no 4/3 pi there. It's just Q. So I just get not Q, it's M. The Q is M in this case. So that get G times 4 pi r squared is equal to, there's no r cubed there, it's just 4 pi Gn M over just M. And then when I divide both sides by 4 pi r squared, I'm going to get G equals, there's no division sign there. Let's cancel that out. 4 pi's cancel out, and I get negative G sub n M over r squared. If I keep that, if I don't keep the negative sign, if I keep the negative sign, then that negative sign goes away and I get the magnitude. So it works. We're going to do the same thing, but for the example I gave starting, the more complicated example, which is to find the Gauss law of gravity. I just did that. Orbit close to a toroidal space station. So a space station that looks like a torus would look like this. When you're really close to a space stations usually look something like this. It's got a bicycle wheel-like appearance, and then it rotates, and people run around on the inside surface. So it looks like a curved city, like Interstellar or some other movies that you may have seen. If you go really close, it looks like an infinite cylinder. So that's the assumption we're going to make. The full solution of the toroidal geometry is pretty complicated, involves elliptic functions and so on. But this infinite cylinder problem is easy to solve. It's no different than a infinite charged cylinder in University Physics 2, with charge replaced by mass. So the calculation is actually pretty similar to that one. So I have this, I have to have a Gaussian surface. I can do both a Gaussian surface inside and a Gaussian surface outside. Now, I've not been told what the nature of the cylinder is. I'm going to assume that it's got a uniform mass density. It may be that the mass is concentrated on the surface like it would be in a real space station. It doesn't matter. So we'll forget about the inside. You can do the inside, but I'm assuming the inside is empty. So we'll just worry about the outside. If it was a solid tube, then you can do the inside and the outside. But the orbits are occurring outside, so might as well stick with the outside. So let's take some distance from the cylinder. Let's call it little r. And the usual arguments can be used for Gauss law. The expectation is that the gravitational field indicated here by green will be radially inwards, while the unit normal vector is going to be like that. So that gives us our negative sign there. And then over here, the normal vectors on the ends are going to be like this, and they will produce a zero contribution because the flux will not leak from there. So the entire flux is trapped from the curved surface only. So the left-hand side of Gauss's law is just going to be the flux through the curved surface of G dot n d sigma. Now we have to take some length. Let's take this length to be L. So that's G times -1 because of the cosine 180 there. D sigma is the area of the cylinder. Well, that's just 2 pi r times L. And that's going to be negative 4 pi G sub n times the integral of the volume density. Let's say it's constant density. So it's just rho times the enclosed volume. That enclosed volume is the radius of the space station, which we'll call capital R. So the area of that space station, cross-sectional area times the height is what we have. So that's the volume density, which I'll call rho naught. It's constant, times the space station's cylindrical volume. So it's pi r squared L. Well, L's cancel out on both sides. And so we have our answer. G, the magnitude, is going to be 4 pi, and 2 pi give me 2. G sub n, rho naught, pi, capital R squared, the L's cancel out, remember, over R. So that's my gravitational field. So I don't want to deal with this expression. So all this stuff in the numerator is a constant. So I'm going to call this gamma over R, where gamma is 2gn rho naught pi R squared. In vector form, G will be negative gamma over R hat. The important thing to notice about this gravitational field, it's not 1 over R squared like it is for a point particle. For a point particle, we observed that the gravitational field is 1 over R squared. This is 1 over R, which means that it's unrealistic. If you go far away, it only falls as 1 over R. So one thing to realize is that as you go further and further away, in reality, the space station first looks like a donut and then it looks like a point. Well, our assumption is that it looks like a cylinder throughout. So this will be like a cosmic string. Cosmic strings are supposed to stretch for large distances across galaxies. So that's the only problem with this assumption. Well, let's solve the problems involved. The first thing we have to do is find the potential energy associated with this gravitational field. Well, that's not difficult to do. So let's get cracking there. Here's my space station, a portion thereof. Very close to the space station, it looks like a cylinder. And then I'm going from one circular orbit, and I'm going to just assume that we have circular orbits. Elliptical orbits will be too distracting at this point. So just take 2 circular orbits. You want to go from one orbit to the other orbit, find the energy needed. Okay, that's the problem. That's our aim here. Let's call this R1, and let's call this R2. So let's say someone accidentally loses a watch or a wrench, and it's making a circular orbit, or the astronaut is making a circular orbit, and the astronaut wants to go to a new radius and make a circular orbit there. So the first thing we can do is find the velocity at a given orbit. Well, that's easy to do. Looking at the space station from above, I'm looking at this picture here. And this is just basic physics. The force of gravity is acting here, and you have your centripetal acceleration in that direction, and the velocity like that. So we can write Newton's second law. Newton's second law says force in the negative r hat direction is equal to mass times the centripetal acceleration, where m is the mass of the astronaut. So when you substitute this into the, well, F is equal to mg. So this is going to be m times g. And that's going to be equal to m times v squared over r. G is gamma over r, magnitude. So that gives me m's cancel out, notice. Doesn't matter who is orbiting. So I get gamma over r equals v squared over r. First surprise, the velocity is completely independent of radius. So the velocity is given by the square root of gamma, which is 2gn rho naught times pi r squared. Does that look like a velocity to you? I don't know. I mean, I get nervous when I see expressions like this. So let's calculate the units. The units of V, this is the physicist coming out in me, is meters per second. Newton's gravitational constant is, how do you get that? Force equals G sub n m1 m2 over r squared. So let's be very basic. This G sub n is going to be Newton meter squared over kg squared, okay? So I'm going to get Newton meter squared over kg squared. Rho is kg per meter cubed. R is meters, R squared is meters squared. So all that is what I have in the square root. One of the kgs goes away, 2 of the meters goes away. So I have square root of, and if one of the meters goes away here also. So Newton meters over kg. Well, Newton meters is joules, and joules is kinetic energy. So it's kg meters squared per second squared over kg square root meters per second. Voila, beautiful. So that's a big surprise. Whether the astronauts here or here, they will orbit with the same speed. Really weird if you think about it. So you don't have a Kepler's third law in a traditional sense, because the time taken to orbit will be proportional to the radius. So it's not the cube of the radius versus the square of the period. You don't have the square cube law anymore. It's just going to be 1 over r. The further you are, the slower it is. But in that fashion. So let's get to answering the questions, though. The total energy, for that you would find a potential energy. So the work done by the gravitational force, Fg, let's find the work done going from R1 to R2. Well, that's just going to be Fg times Fg is acting in, and the path we are taking to integrate to find the work is out. So that's Fg times dr times cosine pi, because of the difference in directions. So the magnitude is gamma over r. So Fg is just mass of the astronaut times gamma over r dr R1 to R2. So that's going to be m gamma, negative m gamma, natural log of R2 over R1, because the integral of 1 over r is natural log. This shows you immediately that there's something weird about this problem. You can't escape. This infinite cylinder will trap you forever. And by definition, this is negative. The change in the potential energy, the work done by gravity is negative change in the potential energy. So that's going to be U1 minus U2 because of the negative sign. So we have found the change in the potential energy. So what did I want? Let me check. Find the energy needed to double the orbit radius. All right. To double the orbit radius, we're going for R2 is equal to 2R1, which means that that's natural log of 2 whenever you see that. So I'm going to get U1 minus U2 equals negative m gamma, natural log of 2. And the energy needed, delta E, is going to be the energy at orbit 2 minus the energy at orbit 1. The energy at orbit 2 is the kinetic energy at orbit 2 plus the potential energy at orbit 2 minus the energy at orbit 1 is the kinetic energy at orbit 1 plus the potential energy at orbit 1. But we already know that the speed is the same regardless of orbit. So the kinetic energies cancel out. So I just get U2 minus U1, so it takes care of the minus sign there. It's just m gamma, natural log of 2. Or now we'll restore gamma to write a grand finale of an answer to conclude the video. This is going to be 2 g sub n, mass density of the space station, pi r squared, mass of the astronaut or whatever is being transported from one orbit to the other, times natural log of 2. And that is the solution to our problem. I hope this video gave you a lot of understanding about Gauss's law and Gauss's divergence theorem. FYI, you can read up. There's a divergence theorem for optics too. Anything that's got intensity that falls off with distance has got a divergence theorem associated to it.